Alright, so I'm going to do a Wikipedia reading of what SMB, aka server message block, is. Have a nice diagram to start things off. At the simplest, it is a client server request response protocol. Basically, servers can make their resources available to clients on the network. So we're talking file systems, printers, mail slots, APIs. So apparently, SMB was originally developed in 1983 by Barry A. Feigenbaum. So Microsoft Word didn't get the correct spelling right there. But anyways, apparently he was at IBM when he developed this and intended to provide shared access to files and printers across nodes on a network of systems running IBM's OS/2. It also provides an authenticated inter-process communication (IPC) mechanism. In 1987, Microsoft and 3Com implemented SMB in LAN Manager for OS/2, at which time SMB used the NetBIOS service atop the NetBIOS Frames protocol as its underlying transport. Later, Microsoft implemented SMB in Windows NT 3.1 and has been updating it ever since, adapting it to work with newer underlying transports like TCP/IP and NetBT. SMB implementation consists of two vaguely named Windows services, and I might as well just show those to you here. I've highlighted it, now it's gray. Let me click off the page and then I'll highlight it in blue. You have for the server ID LANman server, and for a workstation the ID LANman workstation. These are the two vaguely named Windows services. It uses NTLM or Cerberus protocols for user authentication. So sure, you have the implementation and you have the authentication. Well, in 1996, Microsoft published a version of SMB 1.0 with minor modifications under the Common Internet File System (CIFS) moniker. CIFS was compatible with even the earliest incarnation of SMB, including LAN Manager. And just note, LAN Manager is a discontinued network operating system, NOS. The next section is titled Features. It says SMB enables file sharing, printer sharing, network browsing, and IPC parentheses through named pipes in parentheses over a computer network. SMB serves as the basis for Microsoft's distributed file system implementation. SMB relies on the TCP and IP protocols for transport. This combination potentially allows file sharing over complex interconnected networks, including the public internet. The SMB server component uses TCP port 445. SMB originally operated on NetBIOS over IEEE's 802.2 NetBIOS frames, or NBF, and over IPX/SPX, and later on NetBIOS over TCP/IP. But Microsoft has since deprecated these protocols. In Windows, two vaguely named services implement SMB, and so the Wikipedia article is weird for having this redundant fact written again into the article in this features section. So I'm just going to skip down to the part where it says Windows NT 4.0 SP3 and later can digitally sign SMB messages to prevent some man-in-the-middle attacks. SMB signing may be configured individually for incoming SMB connections by the LANman server service and outgoing SMB connections by, yeah, you guessed it, the LANman workstation service. The default setting for Windows domain controllers running Windows Server 2003 and later is to not allow unsigned incoming connections. As such, earlier versions of Windows that do not support SMB signing from the get-go, including Windows 9X, cannot connect to a Windows Server 2003 domain controller. SMB supports opportunistic locking. on files in order to improve performance. Opportunistic locking support has changed with each Windows Server release. So what is this opportunistic locking? In the SMB protocol, it's a mechanism designed to improve performance by controlling caching of network files by the client. Unlike traditional locks, opportunistic op locks are not strictly file locking or used to provide mutual exclusion. There are 4 types of these locks. You have batch locks. They were created originally to support a particular behavior of DOS, batch file execution, in which the file is opened and closed many times in a short period, which is a performance problem. To solve this, a client may ask for an op lock of type batch. In this case, the client delays sending the close request, and if a subsequent open request is given, the 2 requests cancel each other. Next, you have level 1 op locks / exclusive locks. When an application opens in shared mode, a file hosted on an SMB server, which is not opened by any other process or other clients, the client receives an exclusive op lock from the server. This means that the client may now assume that it is the only process with access to this particular file, and the client may now cache all changes to the file before committing it to the server. This is a performance improvement since fewer round trips are required in order to read and write to the file. If another client process tries to open the same file, the server sends a message to the client called a break or revocation, which invalidates the exclusive lock previously given to the client. The client then flushes all changes to the file. Next, we have level 2 op locks. If an exclusive op lock is held by a client and a locked file is opened by a third party, the client has to relinquish its exclusive lock to allow the other client's read-write access. A client may then receive in level 2 op lock from the server. A level 2 op lock allows the caching of read requests but excludes write caching. And the last one is filter op locks. Added in Windows NT 4.0, filter op locks are similar to level 2 op locks but prevent sharing mode violations between file open and lock reception. Microsoft advises use of filter op locks only where it is important to allow multiple readers, and level 2 op locks in other circumstances. Clients holding an op lock do not really hold a lock on the file. Instead, they are notified via a break when another client wants to access the file in a way inconsistent with their lock. The other client's request is held up while the break is being processed. So then they go on to talk more about breaks. In contrast with the SMB protocol's standard behavior, a break request may be sent from server to client. It informs the client that an op lock is no longer valid. This happens, for example, when another client wishes to open a file in a way that invalidates the op lock. The first client is then sent an op lock break and required to send all its local changes in case of batch or exclusive op locks, if any, and acknowledge the op lock break. Upon the acknowledgement, the server can reply to the second client in a consistent manner. So now we get into a section called performance. They say that the use of the SMB protocol has often correlated with a significant increase in broadcast traffic on a network. However, the SMB itself does not use broadcasts. So that sentence might want to be rephrased to say the SMB protocol does not use broadcasts. The broadcast problems commonly associated with SMB actually originate with the NetBIOS service location protocol. And remember, NetBIOS provides services related to the session layer of the OSI model. This allows applications on separate computers to communicate over the network. Wikipedia notes that as an API, as strictly an API, NetBIOS is not a networking protocol. Okay, so NetBIOS functions by broadcasting services available on a particular host at regular intervals. While this usually makes for an acceptable default in a network with a smaller number of hosts, increased broadcast traffic can cause problems as the number of hosts on the network increases. The implementation of name resolution infrastructure in the form of Windows Internet Naming Service, WINS, or Domain Name System, DNS, resolves this problem. By the way, WINS was a proprietary implementation used with Windows NT 4.0 networks, but brought about its own issues and complexities in the design and maintenance of a Microsoft network. Since the release of Windows 2000, the use of WINS for name resolution has been deprecated by Microsoft, with hierarchical dynamic DNS now configured as the default name resolution protocol for all Windows operating systems. Resolution of short NetBIOS names by DNS requires that a DNS client expand short names, usually by appending a connection-specific DNS suffix to its DNS lookup queries. WINS can still be configured on clients as a secondary name resolution protocol for interoperability with legacy Windows environments and applications. Further, Microsoft DNS servers can forward name resolution requests to legacy WINS servers in order to support name resolution integration with legacy pre-Windows 2000 environments that do not support DNS. Network designers have found that latency has a significant impact on the performance of the SMB 1.0 protocol, that it performs more poorly than other protocols like FTP. Monitoring reveals a high degree of chattiness and a disregard of network latency between hosts. For example, a VPN connection over the internet will often introduce network latency. Microsoft has explained that performance issues come about primarily because SMB 1.0 is a block level rather than a streaming protocol. SMB was originally designed for small LANs. It has a block size that is limited to 64 kilobytes. And SMB signing creates an additional overhead, and the TCP window size is not optimized for wide area network links. Solutions to this problem include the updated SMB 2.0 protocol, offline files, TCP window scaling, and wide area network optimization devices from various network vendors that cache and optimize SMB 1.0 and 2.0. Now I'll skip over the history. I haven't said anything about SMB 3.0, so let's start there. It was introduced in Windows 8 and Windows Server 2012. SMB3 brought several significant changes that are intended to add functionality and improve performance, notably in virtualized data centers. So with SMB3, the SMB Direct Protocol, which is SMB over Remote Direct Memory Access, also known as RDMA, is possible. You also have SMB multi-channel. This is multiple connections per SMB session. And then SMB transparent failover. The last thing that SMB 3.0 provided was it introduced several security enhancements, such as end-to-end encryption and a new AES-based signing algorithm. We eventually have SMB 3.1.1, introduced in Windows 10 and Windows Server 2016. This version supports AES 128 GCM encryption, in addition to AES 128 CCM encryption, and implements pre-authentication integrity check using a SHA-512 hash. What I like about this latest protocol, or version I should say, they make secure negotiation mandatory when connecting to clients with SMB 2.0 or higher. Now, I found this interesting. They say the specifications for the SMB are proprietary and were initially closed, thereby forcing other vendors and projects to reverse engineer the protocol to interoperate with it. The SMB 1.0 protocol was eventually published sometime after it was reverse engineered, whereas the SMB 2.0 protocol was made available from Microsoft's Open Specifications Developer Center from the onset. Outset? Outset makes more sense. In the world of third-party implementations, we have something called Samba. So in 1991, Andrew Triggle started the development of Samba for Unix-like systems. He did this initially to implement an SMB server to allow PC clients running the DEC Pathworks client to access files on Sun OS machines. Because of the importance of the SMB protocol in interacting with the widespread Microsoft Windows platform, Samba became a popular free software implementation. As of version 3, which came out in 2003, Samba provides file and print services for Microsoft Windows clients and can integrate with a Windows NT 4.0 server domain, either as a primary domain controller or as a domain member. Samba 4 installations can act as an Active Directory domain controller or member server at Windows 2008 domain and forest functional levels. And the last thing I'll read here today is a paragraph about security. Over the years, there have been many security vulnerabilities in Microsoft's implementation of the protocol. Real-time attack tracking shows that SMB is one of the primary attack vectors for intrusion attempts. For example, the 2014 Sony Pictures attack and the WannaCry ransomware attack of 2017 must have used this vector. And in 2020, 2 SMB high-severity vulnerabilities were disclosed and dubbed as SMB Ghost and SM Bleed, which when chained together can provide a remote code execution privilege to the attacker.